Welcome to this presentation on k-sum paths in a binary tree. In this session, we will explore an efficient solution to the problem using prefix sum and hashmap techniques. Let's begin by understanding the problem statement. We are given a binary tree and an integer k. Our goal is to determine the number of downward only paths where the sum of the node values equals k. A path can start and end at any node, but it must always move downwards. The problem has a few constraints. The number of nodes can go up to 10,000. The node values range from -100 to 100, and the value of k can be as large as 10 to the power 9 or as small as -10 to the power 9. Here is a simple example. We have the binary tree with a root node value of 1, left child value of 2, and a right child value of 3. If we set k to 3, the number of paths with sum equal to k is 2. The paths are 1, 2, and 3. Now let's discuss the approach. We will use a depth first search or DFS to traverse the binary tree. During the traversal, we will maintain a prefix sum, which is the cumulative sum of the node values. At each node, we check if the difference between the current sum and k exists in the hash map, indicating a valid path. We store each prefix sum in an unordered map to efficiently track the frequency of sums encountered during the traversal. This approach ensures we capture all valid paths efficiently. After visiting a node, we backtrack by removing the current sum from the map. Here is a code for the node structure. The node class represents each node in the binary tree, which holds the node's value and pointers to the left and right children. In this part of the code, we define a helper function, findPaths. It performs the DFS and maintains the current sum as we traverse the tree. The function checks if current sum k exists in the hash map, and if so, we add the count of such paths to the result. We update the prefix sum map and recursively call the function for both left and right children of the node. After visiting the node, we backtrack by decrementing the current sum in the map. The sumK function is the main function that initializes the prefix sum map with 0 and counts the number of valid paths by calling the findPaths function. The result is returned once all paths have been explored. Now let's analyze the time and space complexity of our solution. The time complexity is big O of n, where n is the number of nodes in the tree. This is because we visit each node exactly once. The space complexity is also big O of n in the worst case, as the hash map may store up to n prefix sums in the case of an unbalanced tree. Here is an example execution of our approach. We start at the root node with value 1 and initialize the current sum to 1. We then remove to the left child node with value 2, updating the sum to 3. Since current sum k is 0 exists in the map, we have found a valid path. We then move to the right child node with value 3 and again find another valid path with sum 3. So in this case we found two paths with sum equal to k. To summarize the key takeaways, we have implemented an efficient solution using prefix sums and a hash map. This method handles large inputs effectively and is memory efficient through backtracking. Additionally, it works for both positive and negative values of k, making it a robust solution. Thank you for your attention. If you have any questions or doubts, please feel free to ask. Let's discuss any points you are unsure about. Welcome to the presentation on the clear digits problem. In this presentation, we will explore an algorithm to efficiently remove all digits from a given string. The problem is solved using a stack data structure. Let's dive into the details. The task is to remove all digits from a string by performing the following operations repeatedly. We need to delete the first digit in the string and the closest non-digit character to its left. The objective is to return the string after all digits are removed. Let's take a look at some examples to understand the problem better. In the first example, we have the string ABC. Since there are no digits in the string, it remains unchanged. In the second example, the string is CB34. Here's how the operation works. First, we delete 3 and C, resulting in the string 4. Then we delete 4 and B, leaving us with an empty string. Now let's look at the approach to solve this problem. To solve this problem, we need to use a stack. The idea is to loop through each character in the string. When we encounter a digit, we pop the top of the stack, which removes the closest non-digit character to the left of the digit. This ensures that the stack will contain only non-digit characters and we can easily build the final result. Let's move on to the algorithm used for this solution. The algorithm begins by initializing an empty stack. As we iterate through each character in the string, we check if it is a digit. If it's a digit, we pop from the stack. If it's not a digit, we push it onto the stack. After processing all characters, we build the result string by popping elements from the stack. Now let's look at the actual code implementation. Here's the first part of the code. We begin by defining a class called solution and a function clearDigits that accepts the input string s. We initialize a stack to keep track of the non-digit characters. As we loop through the string, we check if each character is a digit or not. If it's a digit, we pop the stack, removing the closest non-digit character. Otherwise, we push the non-digit character onto the stack. In the second part of the code, after processing all characters, we construct the final result string by iterating through the stack and adding the characters to the result in reverse order. This ensures that the characters appear in the same order as they were originally in the string. Let's break down the code. Initially, we loop through the string character by character. If the character is a digit, we remove the closest non-digit character by popping the stack. If it's not a digit, we add it to the stack. Once all characters are processed, we create the result string by building it from the stack. Stack ensures that we maintain the correct order of non-digit characters. Let's analyze the time complexity of the algorithm. The time complexity is big of n, where n is the length of the string. Each character in the string is processed once, and each character is pushed and popped from the stack at most once. Therefore, the overall time complexity is linear. The space complexity is also big of n, as we use a stack to store the non-digit characters. There are a few edge cases to consider. If there are no digits in the string remains unchanged. If the string consists only of digits, the result will be an empty string. And if the string has alternating digits and letters, all digits will be removed, leaving only the non-digit characters in the string. In conclusion, this problem is efficiently solved using a stack. The algorithm processes the string in linear time and uses space proportional to the length of the string. By using a stack to manage the non-digit characters, we ensure that digits are removed in the correct order. This approach provides an elegant and efficient solution to the problem.